In this lecture module, we'll spell out our effective decision procedure for categorical syllogisms in both Boolean and Aristotelian logic in fair detail, after which we'll go through a few practice problems and rehearse the procedure. So by following this three-step procedure for testing your arguments for validity, you're always going to get an answer, and the answer will always be right so long as you follow the procedure correctly. You'll always start in Boolean logic. You'll have a separate premise diagram and a separate conclusion diagram. You're going to symbolize both of your premises on the premise diagram, and then what you need to make the conclusion true on the conclusion diagram. Then you want to compare these diagrams. Is what you entered on the conclusion diagram also present on the premise diagram? If your answer is yes, then the argument is valid. It's not just valid in Boolean logic, it's valid in both Boolean and Aristotelian logic. If the argument is invalid, then you have to test for Aristotelian validity. When we test for Aristotelian validity, we go back to our premise diagram. But now, because we have more premises, more classes, we just want to use a general rule for assigning our existential circles, our Aristotelian circles. We're going to add a circled X to any premise diagram circle that has 3 of its 4 areas shaded, so that there is only one area where you could put that X, and it's the only X that would be in that circle. Now you might be wondering, why do I need to put circled X's only in classes where 3 of the 4 areas are shaded? And the answer to that is actually pretty straightforward. Only if you can put an X in a single area and not on a line does it have the potential to make an argument valid. Whenever you put an X on a line, there's at least 2 ways for that X to make that premise true. As a result, both of those ways would have to make the conclusion true. And so only when we have an X in a single area, only when it's not on the line, does it have the potential to make an argument valid. And that's why we put our circled X's only in classes with 3 of the 4 areas shaded, so that we can put it in one determinate spot so that it might make a difference. So we'll add a circled X to the sole unshaded area of any partially shaded circle in our premise diagram only. Then we're going to check and see, after modifying our premise diagram, is what we need to make our conclusion true? Is what's in the conclusion diagram present in the premise diagram? If it isn't, then the argument is invalid in Aristotelian logic as well, and you can stop. If it's there, you're going to have to decide whether or not this argument satisfies the Aristotelian assumption. You go to the class that gave you the X that made the argument valid formally, and then you ask yourself, does that class actually have a member? Is it a good Aristotelian class? If it is, then the argument is valid in Aristotelian logic. If it isn't, then the argument commits the existential fallacy. Let's practice. Suppose we have an argument that says all beer swilling goons are people who buy season tickets. Some people who buy season tickets are Maple Leaf fans. Therefore, some Maple Leaf fans are beer swilling goons. We'll begin by drawing a premise diagram, then a conclusion diagram. Now remember, when we label our diagram, the minor term, the subject of our conclusion, goes on the bottom left. The major term, the predicate of our conclusion, goes on the bottom right. And the middle or bridging term, the term that's in both premises, that goes up top. Once we've labeled our premise and conclusion diagrams, then we want to start representing what minimally has to be true in order for our premises and our conclusion to be true. In this argument, we have one universal premise. We always start with the universal premise. We always start in Boolean logic, and so we want to symbolize what minimally would have to be true in order for all beer swilling goons are people who buy season tickets to be true. So we go down and we say, okay, beer swilling goons, that's our B class, bottom right. People who buy season tickets, that's our middle or bridging class, that's up top. If all beer swilling goons are people who buy season tickets, and I'm a good Boolean, so I don't know if there are any beer swilling goons, and I don't know if there are any people who buy season tickets. What I will know is everything, if there is anything, that's in that B class will also have to be up in the P class. And so any part of my B circle outside of P would have to be empty. So I'll shade it in to indicate there can't be anything in that area. Now it's time to look at my particular premise. Some people who buy season tickets are Maple Leaf fans. So there's at least one person who buys a season ticket who is also an M, a Maple Leaf fan. So that intersection between P and M is where I'm going to put my X. Since it has two areas, M and P only, and M and P and B, and nothing about our premise tells me which area to put it in, I put it on the line. Then I turn to my conclusion diagram. My conclusion says there's at least one thing. It is a Maple Leaf fan and it is a beer swilling goon. So there's going to be an X. It's going to go in the intersection between Maple Leaf fans and beer swilling goons. But again, I have two areas there. I could have just Maple Leaf fans and beer swilling goons without being a person who buys a season ticket, or I could have all three. Since my conclusion doesn't discriminate between those two cases, I put my X on the line like that. Now I look at my conclusion diagram and I say I have to have an X somewhere in that intersection between M and B. I look over at what the world would have to be like in order for my premises to be true, and I ask, will making my premises true guarantee that my conclusion is true? Now I do have an X right here, and that's right on the line, but that means there's at least one way for this to be true, where there's an X over here and not in here, as well as one way for this to be true where there's an X here. As a result, it's possible for the premises to be true without guaranteeing the conclusion is true. That would be the case if this was just over there. So as a result, it's possible for my premises to be true without guaranteeing my conclusion is true, and that makes this argument invalid in Boolean logic. So I want to check and see if it's valid in Aristotelian logic. I look over at my premise diagram and I say, is there any circle that doesn't have an X in it already, that has three of its four areas shaded? There isn't a circle in my premise diagram that has three of its four areas shaded. The closest is that B circle that has two of its four areas shaded. So I don't modify my premise diagram. If I'm not modifying my premise diagram, then my argument will be invalid in Aristotelian logic as well. Let's try another case. Suppose I have an argument that says some comic book characters are fictional objects. All comic book characters are characters that excite the imagination. Thus, some characters that excite the imagination are fictional objects. Again, I'll put in my premise diagram and my conclusion diagram. My minor term, the subject of my conclusion, goes in the bottom left. My major term, the predicate of my conclusion, goes in the bottom right. And the middle or bridging term, the term that's in both of my premises, comic book characters, I'll put that up top. Now that I've got my diagrams drawn and labeled, I go to my premises. My first premise that I'm going to do is that universal premise. It says all comic book characters are characters that excite the imagination. So I'm being a good Boolean. I say, I don't know if there are any comic book characters. I don't know if there are any characters that excite the imagination. But what I do know is everything that's in that C class, everything that's a comic book character, if there's anything, also has to be in that E class, the characters that excite the imagination class. So any part of C that is outside of E would have to be empty if that premise is true. So I shade in those areas of C outside of E, and that is what minimally would have to be true in order for that universal affirmative premise to be true. Now I want to do my particular premise. Some comic book characters are fictional objects. There's at least one thing. It is in the comic book character circle. It's in that C circle. It is also in the fictional object circle in the F circle. That means it's got to go somewhere in the intersection between C and F, that area that is in both of those circles. Part of that area is already shaded in, the C and F, but not E. And so I'm going to have to put my X in the only area that is still open, in the intersection between all three. Now I go to my conclusion diagram. Some characters that excite the imagination are fictional objects. There's at least one thing. It is in the E circle. It is also in the F circle, so it goes in that intersection between E and F. Again, it doesn't say whether or not it's also a C or whether it's not a C. And so I put it on the line because there are two possibilities. Either one would make my conclusion true. Now, I look at my conclusion diagram and I say, what I need to guarantee my conclusion is true is an X somewhere in that intersection between E and F. It could be a C or it could be just an E and an F. It doesn't matter where it is as long as it's in that intersection. I look over at my premise diagram and sure enough, I do have an X in the intersection there between E, F, and C. That X is an X that's in the intersection between E and F, and hence I guarantee that my conclusion is true if my premises are true. And so this argument is valid in Boolean logic, and because it's valid in Boolean logic, it's valid in both logics.